Hi, my name is Ivo and I'm doing research into Nikola Tesla's radiant energy, which is related to impulse electricity. In my research, I've come to realize that two bifilar pancake coils can act as the plates of a high voltage capacitor, which makes it possible to discharge that coil capacitor without a spark gap by using a coil discharge voltage impulse. To make a coil capacitor, you also need a dielectric material in between the plate coils. Air can be used, but epoxy is a better choice as it has a dielectric constant of around 3, which makes the capacity 3 times larger. I'll now show you part of the build process of that coil capacitor. I've got a bucket here, and this is a 10-liter bucket for cleaning. I cut the top off because it was too wide for the vacuum chamber. This bucket now fits into my vacuum chamber, and inside I have the L1 and L3 coils. On top of that will be the L2 coil, like so. And then this hole can be placed inside the vacuum chamber, poured full with epoxy to the right level, and then vacuum the air bubbles out. So there's a pure epoxy inside of the coils. Let me get the coils out right now. Put the bucket aside. So this L2 coil has a distance holder. These are 3 times 5 millimeters nylon rings, which are hollow, and they create a 15 millimeter distance between L2 and L3, which is ideal for tuning the impulses of L2 to its current maximum and the voltage minimum. Here you can see L1 and L3. I tape them together. And I put some nylon rings on the bottom to create some distance from to the bucket, because I've got the windings here that are pretty thick, because I used 2.5 millimeters squared copper wire, speaker wire, around 6 meters. I say around because it's not equal mass for L1. I only use equal mass for L2 and L3, which are exactly the same coils. So L1 has thicker wire, and therefore it has less windings, and because it has less windings it has less inductance, and this gives a higher resonant frequency for L1. And since the impulse that it generates is a half wave of the resonance of L1, I have a very fast impulse with very high voltage. I measured the impulse to around 280 nanoseconds duration. The L3 coil has more windings because it has 1.5 square millimeters in diameter, and it is equal in size to the L2 coil, which is then put on top. So if you look from the side, here's L1, L3 and L2. L1 produces the impulse, L3 is parallel resonant, and L2 is series resonant. So L2 has low impedance and L3 has high impedance. And this will together form the coil capacitor, because the L2 coil will be given a DC offset of 3000 volts positive, and the L3 coil is grounded, so that creates a 3000 volt difference between L2 and L3, which act as the plates of a capacitor. Now when I measure this with a capacitance meter, this gives a capacity of around 31 picofarads with air in between them. So that's very low, and that's why I need a very high voltage. But I can make this capacitor a lot stronger if I use a dielectric medium in between those coils, and that's why I will cast them in epoxy, because it has a value of around 3, where the dielectric constant of air is only 1. So 3 times as much capacitance basically. I tested some capacitors which I made with epoxy and a titanium dioxide mix. This is a 50% weight ratio, and that gave a pretty good increase in comparison with the pure epoxy capacitor, which I've got here. I've got a few other capacitors. So this is pure epoxy. As you can see, there is a plate inside here, 2 plates. These are copper plated PCBs, which I use as capacitor plates, 5x5, so I can make a comparison. So pure epoxy had 22.3 picofarads, while the 50% weight ratio titanium dioxide had 38 picofarads. So that is a good increase of around 1.7. But this is very messy. As you can see, this is I believe a 33% titanium mix, which still is very good, but it still has some troubles with the air inside. And this one only had 28.7 picofarads. So it's just a small increase of capacitance. And this with a lot more titanium epoxy. This mixture, which is 50-50 titanium dioxide and epoxy, was very hard to make properly because it looks smooth, but there's a lot of air still inside of this, because when I put it in the vacuum chamber, it created foam, but the bubbles wouldn't burst. And I think I need higher temperatures to make it. And with a project with these big coils, yeah, I would need something that is very controllable. So I won't do it this time. I'll use pure epoxy for now, because it will increase to, I hope, enough capacitance. I will cast this into the bucket, and I'll put it into the vacuum chamber and let it harden out. I'll probably make a cast with 2 times around 600 milliliters of epoxy. And the first I will cast this coil into epoxy until it's flooded, and then I'll put this one on top to be sure that it's fixated. So this one won't be inside of the epoxy the first time. Then when it's hardened, then I'll put the next layer of epoxy on top and vacuum chamber it again, and then it will be fully inside of the epoxy. And the reason that I do that is epoxy becomes very hot, and if this layer is too thick, which it is, it will be so hot that it will deform and cause all kinds of problems. The information in this video is part of my open source research into impulse electricity. This means no patents can be applied. You can fund my research by giving a donation on my PayPal account, which is listed below. Please share this video with others that might be interested. Subscribe and like this video. This really helps out. Thank you for watching, and see you next time.